So good morning. No, not good morning. Good afternoon, everyone. So this is a recording of the office hours for Tuesday, October 18th, the day before the exam. So we'll proceed pretty much just like how we did this morning in terms of if you have a question on a specific topic, then I can go on about that topic. Or if you have a homework problem that you were trying and you couldn't figure out how to do it, then we can do it together. So with that in mind, does anyone have anything to start us off with? Maybe I can refresh you on what are the topics. So we go from 1.4, that's functions, okay, plugging into functions, finding the domain and range of functions. We talked about properties of functions, okay, whether a function is increasing or decreasing, or constant, things like that, or whether a function is even or odd. Transformations of functions, so moving functions up, down, reflecting. Any of this sounding interesting so far? Or like something that might have given you trouble on like a quiz or a homework before? Okay, do you want me to just take the reins here? Okay. All right. Why don't we just go in order? We talked already about 3.1. And we talked about some other more recent stuff like rational functions and polynomial zeros, dividing polynomials. Why don't we focus on the previous half? So something like 1.4 to 1.8. So we'll do maybe properties of functions. Let's see if there's any good problems in here. Max and min. Okay, this one's fun. All right, let's talk about even and odd functions. So follow-up question. What does it mean if a function is even? Question for the class.
Symmetrical over the y-axis.
So I hear symmetric about the y-axis. About the y-axis. Okay, so in other words, it looks symmetric about the y-axis. So the y-axis is the one that goes up and down. So if we're symmetric about the y-axis, then maybe it could look something like this, right? This could be an even function, right? How can we tell that it's even from looking at the graph? We can check and look, does it look like it is symmetric about the y-axis? That's one way in which we can check if a function is even visually. So this is how we check visually. How we check visually. But what if instead of giving me the graph of the function, they give me a function like f of x equals 37x to the 4 minus x squared plus 3. Then how do I know? We have one definition of what it means for a function to be even. Its graph should be symmetric. So graph is symmetric about the y-axis. What if they give us an equation like that? Can we still tell, or do we need to draw the graph?
Just look at the power of the leading term.
The power of the leading term. How do we feel about that? Do we agree? As long as the power of the leading term is even, then the function is even? Hands up for agree. Hands up for disagree. Okay, I'm having some disagreement. Can you?
It's like the largest power, because they could put like 37x to the 4th minus like something x to the 5th.
Right. So I think that when we say leading term, okay, it doesn't necessarily refer to the term in front. Leading term refers to the term of highest degree. So in that sense, I think you're talking about the same thing. But there's actually a little bit more of a snag than just the leading term. Yes?
So you plug in negative x, and then if it's equal to x, then it's even. If it's equal to negative f of x, then it's y.
Correct. So what does symmetric about the y-axis mean algebraically? What it means is that if I plug in x versus if I plug in negative x, I get the same thing, right? Because what is this? Here's the point x. Where is the point negative x? Well, it's on the opposite side, right? And for it to be symmetric about the y-axis, what we need is for the height of these 2 points to be the same. That's what we need. So this is the point x comma f of x. And this is the point negative x comma f of negative x. For the graph to be symmetric, the height needs to be the same, which means that the y-coordinate of this point needs to be the y-coordinate of this point. Those two need to be the same, which means that f of x needs to be equal to f of negative x. This is how we check whether a function... Oh my god. Okay, that was unnecessary. Let's put the volume all the way down. And let's check to make sure that's not a confused student. It's not. Okay. So, this is how we check. And actually, it is important because I think in a lot of scenarios, your just check the leading term would probably work, but there's some scenarios where it wouldn't. For example, if I take f of x to be the sum of an even function with an odd function, if I do something like this, then it's not actually going to be even though the highest power is even. So how do we check? We check using this. So let's check whether this function is even or not. Well, what we should do is first plug in x. When we plug in x, we get x to the 4th plus x cubed, right? That's what the function rule literally says. But what happens if I plug in negative x? I would get negative x to the 4th power, and then I would add negative x to the 3rd power. The first thing, since I do 4 multiplications of a negative number, it becomes a positive number, right? So this is x to the 4. This is what we're checking, by the way. This equality is what we're checking. So we get x to the 4, and then since I multiply a negative number times itself 3 times, it stays negative. So these two things are actually not equal to one another, are they? Why not? Just take x equals to 1. If I do 1 plus 1, that's 2. If I do 1 minus 1, that's 0, right? Are there any seats left? There's 1 left. 2 left. Okay, so the way we check evenness is by checking this algebraic property, okay? So we just plug in x, we plug in negative x. If we get the same thing, even. If we get something different, odd. This is why when we have a power function like f of x equals x to the p, okay, if p is an even number, then the function will be even, because x to the p, when is x to the p equal to negative x to the p? This is true if and only if p is an even number. Okay? Is that clear? Yes?
So basically, if there's like an odd exponent, it's not going to be an even function.
Yeah, if you have a polynomial, okay, so if the question is, if the polynomial contains an odd exponent, can it be even? Can it still be even? That's your question?
Yeah.
Let me think about that. I would say I don't think so. I think that the answer here is no. So yes, if you see something like x to the fourth minus x cubed, you can already tell that it's not going to be even because it contains a term which has an odd degree. Yeah, I think that is. I'm like 99% true that this is the answer to this question. Okay. But you can always check. I mean, it's not too hard to check. You just plug in x, you plug in negative x. If it's the same, it's the same. If it's not the same, then it's not the same. And if it's opposite, then we call the function odd. So next up is odd functions. Odd functions are symmetric about what? So we say, well, these ones are symmetric about the y-axis. Let's take a look at a function that would be symmetric about the x-axis. If I had a function that was symmetric about the x-axis, what would it look like? It would look like something like this. But guess what? Is this a function? No, why not? It fails the vertical line test. So this wouldn't actually be a function. So we're not going to be talking about functions which are symmetric about the x-axis. There's one other type of symmetry. There's y-axis, there's x-axis, and there is the origin. About the origin is what we're going for here. Okay, so odd functions are symmetric about the origin. So for example, you can take something like this. Okay, this is the function f of x equals x cubed, right? So what do I want to check with an odd function? Well, I need to think about what does the symmetry mean? If I plug in x and I get this point, right? This point is the point x comma f of x. The way we get the height is by plugging the x value into the function. What about if I plug in negative x? What should I get when I plug it in? I should get negative x comma f of negative x. And now we can see that there must be a relationship between this number and this number. What is that relationship? They should be opposite, i.e. f of x should be equal to what? Sorry? Sorry? Yeah, negative f of x is what we want. Sorry, not negative f of x. Negative f of negative x. Right? Meaning that this height is the negative of this height, right? Which means also that this height is the negative of this height. They're negatives of each other, right? You can move the negative sign over here if you want. Okay, so this is what we want to be true for an odd function. Okay, for an odd function. Okay, so let's see this function. Let's try this function. Let's try something like this. By the way, unlike integers, okay, functions do not have to be either even or odd, okay? When we think about numbers like 1, 2, 3, 4, 5, they're either even or they're odd. For functions, it's possible that you have neither even or odd, okay? So let's see an example. Let's check if f of x equals x cubed plus 1 is even, odd, or neither. Okay, so we know we don't really need to check whether it's even, or do we, right? Because we decided if there's an odd power, it's definitely not going to be an even function. But let's check it anyway, just for fun. Let's prove algebraically that it is not an even function. Well, f of x is x cubed plus 1, which is not equal to f of negative x, which is going to be negative x cubed plus 1. Okay, so this tells us that the function is not even. Function is not even. Can you close that door for me, please? Thank you. Let's do another check. Let's check if it's odd. Well, what are we trying to check if it's odd? What we want to check is f of x, that's x cubed plus 1. We want to check, is this equal, question mark, is it equal to f of negative x, negative f of negative x? What happens if I take negative f of negative x? Well, I would take f of negative x and make it negative, which would be x cubed minus 1. So, oh crap. We have a situation here where we tried to check if it's even, and we got something which was not equal to the other thing. So it's not even. Then we tried to check if it's odd. So we check whether f of x is equal to negative f of negative x. And x cubed plus 1 is not the same as x cubed minus 1. So what can we conclude? It's not odd. So our conclusion is f of x is neither odd nor even. Okay? So this is how we check even and oddness for a function. Plug in negative x. If it's equal to f of x, then we're even. If it's equal to the negation of f of x, then our function is odd. Okay, so if you have a picture, you can just observe the natural symmetry, right? You can just look at the symmetry. But if you don't have a picture, you need to use the definition. So for even, that definition is f of x equals f of negative x. For odd, that definition is f of x equals negative f of negative x. Okay. Any questions on even and odd functions? Okay, yeah. Okay, let's look at a couple of these graphs for fun. You're not going to see this on the recording, but we're looking at some pictures. What do we think about this function? Even?
No.
Odd?
No.
Why not?
It's not symmetric.
Not symmetric. If it was odd and it was symmetric, probably ought to go through the origin, right? Or else it's going to be split. Okay, what's next? This one, what do we think? Even? No. What about odd? You agree with odd? Yes, because we have this anti-symmetry, or symmetry about the origin, right? So on the right side, okay, this point has height, whatever this is, -1, right? But on the left side, if we go the same distance from the origin on the x-axis, okay, so we're talking about from here to here, the same distance in the opposite direction, the height of the point is 1 instead of -1, right? So that's what it means to be symmetric about the origin, okay? The height should be opposite on the other side. All right, what do we think about this function?
Even.
Do we agree with that? Okay, yeah, I agree too. I think this is an even function. Is it a problem that the point there where it crosses the y-axis is up at 0, 1? No, it doesn't matter, right? What we need is for a point on the right side, like if we go over to x equals 1, the height is 1. If we go to x equals -1, the height should be the same as what it was before. It's also 1. Or not 1, I guess it's a half, right? Okay. So that's the idea. Okay, what is this? Could this function possibly be even or odd? What do we think? Is this one giving us issues? Hands up for even. Okay, what do we need to have if it's even? It should be symmetric about the y-axis, right? So if I have a point here at negative 4, comma 4, what should be the height of the function when x is equal to 4? So for an even function, let's see here. So let me recreate this here. Okay. Something like this. Okay, so here we have a function which comes in like so. Actually, I think we have a hole here and a hole here. Okay, so what is this point? This is the point negative 4, and this is the point negative 4, 4, right? On the other side, we've got what? 4, and this is the point 4, comma negative 4, yes? So even means f of x equals f of negative x. So what is, let's check whether this is true for 4. Is f of 4 equal to f of negative 4? Question? We agree or not agree? All right, someone be brave. What is f of 4? It's negative 4. Is that the same thing as f of negative 4? Which, what is f of negative 4? F of negative 4 is 4. Are these two things equal to one another? No, they are not equal to one another. So this one's going to be not even. Okay? If it was even, then this point would have a corresponding sister point right here. Okay? But it doesn't, so it's actually not even in this case. All right? Is that clear? All right, how about oddness? What is true if the function is odd? What should be true? Not f of x equals f of negative x, but something similar. How should I change this? I need to add a negative here, or on the other side if you want, just not on both. So this means that for every point like on the left side, which has a certain height, there's a corresponding point on the right side which has that height but negative. Yes? So this one, I think, is going to be true. Yes, this is an odd function. Is that clear? Okay, I think it's a little bit confusing when you start throwing in piecewise functions like this, you know, piecewise functions as opposed to like polynomials, right? With polynomials, it's maybe a little bit easier to see. But you can have all sorts of weird looking functions. Like, for example, you could do this function would be, yeah, sorry. Like, for example, you could do this function. This function is odd. Okay, why is it odd? Because for each point, which is a certain length away, okay, a certain length away from the origin, there will be a corresponding point, which is the same length away from the origin in the opposite direction, whose height is the negative of whatever this height is, right? This height is this much, and this height is this much. It's the opposite. And this distance is the same as this distance, okay? So you can cook up some very strange looking odd functions, okay? Or even functions if you use piecewise functions, right? Okay, any more questions on even and oddness? Okay, doesn't seem like there are, so let's move on to a new topic. Let's see. Okay, here's a problem on average rate of change. So, average rate of change, the function is f of x equals negative 3x plus 7 from, this is boring, I'm going to make it 3x squared, from a equals 1, negative 1, to b equals 3. Okay, so let's try to find the average rate of change of this function from a equals negative 1 to b equals 3. So, is there anyone that remembers what is the formula for the average rate of change of f of x from x equals a to x equals b?
F of b minus f of a over b minus a.
Good. F of b minus f of a over b minus a. And does this kind of form of a mathematical statement bring anything to mind? Yeah, maybe slope, right? F of b, that's an output. This is like a y2 minus a y1 over a x2 minus a x1. This is the slope of a line. Which line? It is the line that if you plug in a and you go to the point a comma f of a, and you draw a line from that line to another point. This point is the point b comma f of b. And if you were to draw a line passing through these 2 points, then the slope of that line would be this number. Agree? So, it's nothing but a slope formula. So I like it when I require my students to memorize less. If you know how to do the slope formula and you know how you get the point on a graph of a function, i.e. the height should be what you get when you plug the x value into the function, if you know those 2 things, you can always rederive the average rate of change formula without doing any work. Okay, so this is the average rate of change. So let's do it for our problem. Well, what is b in our case? It's 3. And a is negative 1. So I need to do f of 3 minus f of negative 1. And I need to divide that by 3 minus negative 1. Okay, I just put b where b goes, and I put a where a goes. And then we compute. So f of 3, the way I find out that number is by plugging in 3 for x in the function. So I get negative 3 times 3 squared plus 7 minus what I get when I plug in negative 1, which is negative 3 times negative 1 squared plus 7. And this is all being divided by 4. So let's go ahead and clean this up a little bit. We get negative 27 plus 7 minus, okay, negative 1 squared is 1 times negative 3 is negative 3. And then plus 7 all over 4. So simplify a little bit more. It's 20 minus negative 3 plus 7 is 4. Divide that by 4. And I get 16 over 4, which is 4. Okay. So what is this showing? Well, we know how to graph a function like that. Let's go ahead and do it. What kind of picture is it going to create if I have negative 3x squared plus 7? This is a quadratic function, so its graph looks like what? Yeah, parabola. Does the parabola go like this or like this? Yeah, it goes down. Why? Because the a value here is negative 3. The coefficient which is attached to x squared is negative 3. Since that's a negative number, we know that our function can't look like this. It has to look like this. So it's the graph. You could also think of it as the graph of x squared, but what? We have a reflection about the x-axis, we have a vertical stretch by a factor of 3, and we have a vertical shift up 7. So all told, what will this look like? It will be an even function, and it will start at 7, and then it will go down like this, right? It will go down like this. So if you plug in negative 1, what did we get when we plugged in negative 1? We got 4, right? When we plugged in negative 1, we got 4. So that's I missed something. I missed a negative sign here. This should have been negative 20, right? Negative 27 plus 7 is negative 20. And then minus 4 would not be 16. It would be negative 24. And then this should be not 4, but negative 6. Sorry. Okay, so when I plugged in negative 1, the height was 4. So that's this point. Here, negative 1, 4. Now what's the other point? 3, when I plug it into the function, I get negative 20. Okay, so that's like somewhere way down here, right? So 1, 2, and then 3 is way down here at 3 comma negative 20, yes? So if I were to draw a line between those 2 points, it would look like this. And the slope of that line would be negative 6. Okay, so this is the visualization of average rate of change. The formula for average rate of change is f of b minus f of a over b minus a. Any further questions on average rate of change? Okay, then let's do something else. Well, let me ask again. Are there any specific topics that anyone wants to cover that we haven't talked about yet, or that we have talked about that you want more details? Yeah.
Could you do like a simplified version of what you like the one we were all confused in class today?
Sure. You want a simplified version of the rational problem. Okay. Yeah. Sure. Okay, let's take a look. All right, let's try this one. So we have f of x equals to negative 4x plus 1 divided by x plus 3. And it says to graph it as a translation of 1 over x and identify vertical and horizontal asymptotes and state the domain and range. State the domain and range. Okay, so that's the problem. I'm going to show you an additional step which is going to be the following. What is my additional step going to be? My additional step is I'm also going to show you how to graph this without using graph normally, I guess. So 2 different ways to graph this function. We can view it as a translation of 1 over x, okay, and we can apply our theory of like, oh, shift up or left or reflect or whatever. Or we can also just graph it using the theory which we were talking about this morning, okay? Namely, we would identify the vertical asymptote, we would identify the horizontal asymptote, and then we would identify the behavior, find any zeros, and the y-intercept, and so on. So we'll do all 2 of those ways, and then we'll answer the other questions. Okay, so let's first think of this as a translation of 1 over x. So by translation, well, really translation, it should be transformation, right? Transformation. Did they use the word translation in the homework? They did. That's kind of strange. Well, anyways, let's start by trying to view it as a transformation of 1 over x. So, transformations of 1 over x. I can do stuff like add a number, right? Or I could do stuff like multiply by a number, right? But is there anything that's kind of particularly different about this function from a function which is a translation or a transformation of 1 over x? Yeah, there's an x in the numerator of this guy, right? Which means we haven't just multiplied by numbers, added things, or made it negative. We've introduced like a whole other variable. So how am I supposed to consider this as a transformation of 1 over x? This is confusing to me. Can someone help me out? Yeah? Yeah, you can do long division, right? Actually, it's going to be pretty short. What goes on the inside? The numerator, negative 4x plus 1. And on the outside, we put x plus 3. And so what is going to go right here? Negative 4. That's what we get when we divide negative 4x by x, which is the first term here, yeah? So if I do that, I get negative 4. So then what do? I multiply down, and I get, what? Minus negative 4x minus 12, right? Okay, so if I subtract that, these ones cancel, and I'm left with 1 plus 12, which is 13. Okay, so f of x, which is negative 4x plus 1, divided by x plus 3. Since we have done this long division, we know that we can rewrite it. How can I rewrite it? Negative 4, good, plus 13 over x plus 3. Okay, that's because we have a remainder here, right? We have a remainder. Okay, so now I have this, and now it looks like a transformation of 1 over x, right? It looks like a transformation of 1 over x. What are the transformations that are present here? Let's list them. Someone give me one. What are the transformations? I'm coming from 1 over x. What did I have to change about 1 over x in order to turn it into this business? I have a vertical stretch by a factor of what? Negative 4 for vertical stretch. I think in this case it's going to be 13, because we're taking this and we're multiplying by 13. That's how we get it to look like 13 over x, right? So what is this negative 4 contributing? Reflection? It's not a reflection. What is this going to cause?
Vertical shift down.
Very good. A vertical shift down 4. Any others?
Horizontal shift to the left 3
Yeah, horizontal shift to the left. 3 units. Left 3. Okay. And that's it. But here's a banger of a question for you. Which one should I do first?
The stretch.
Horizontal symmetry.
Is that your final answer?
No.
No, we better go back to that rainbow slide, shouldn't we? Let's go back to it and review that. Oh, it wasn't chapter 2, was it? It was chapter 1. It was a long time ago. Here we go. Order matters. What does it say to do first? Horizontal shift, then horizontal stretch. Then vertical stretch, then reflections, then vertical shift. So which ones do we have? We have horizontal shift. We have vertical stretch. And we have vertical shift. So that's the order that we should do them in. Okay? So this is something that you might want to memorize somehow. You could have a mnemonic device for it or something. Yeah, I don't know. It's like HHVRV, but then you need to remember that the stretch, but the horizontal shift comes before the horizontal stretch, but the vertical stretch comes before the vertical shift. So I don't know if there's like a good mnemonic device for this other than just to memorize it. I mean, I guess one way to think of it is you're kind of working your way from the inside to the outside, right? What's the first thing you do is the horizontal shift. And then you do the horizontal stretch. And then what do you do next? You do the vertical shift. And then the last thing you do is the reflections, and then the vertical shift is the very last thing. So it's kind of inside to the outside, with the exception of the reflections coming after the vertical stretch. If you had a horizontal reflection, you would do... Okay, well anyways, I suppose it doesn't really matter how it gets memorized, but it's necessary, nay, imperative to memorize this. Okay, so which one comes first? Horizontal shift. Which one comes second? Vertical stretch, and then vertical shift. Okay, so now it's in the correct order. Okay, so let's do it. Let's take a look at the graph of... We're going to do a lot of graphs here. Let's first draw, what does the graph of 1 over x look like? What does the graph 1 over x look like? So this is one of the ones we should definitely memorize. Okay, so 1 over x, it has a vertical asymptote when x is equal to what? What is going to cause 1 over x to blow up?
Divide by 0.
Yeah, divide by 0, right? So if x is 0, that's when we're going to have a vertical asymptote. So this one we have a vertical asymptote here. So we need to know, does 1 over x go down and up, or does it go up and then down, or is it up on both sides, or is it down on both sides? What should it look like? Here's option 1. Here is option 2. Here is option 3. And here's option 4. Which one do we think? Pink, blue, orange, or green? Yeah, I think I'm hearing pink, and I agree. Why should it be pink? Because if x is positive, which it is on the right side of the x-axis, then 1 over x will be what kind of number?
The opposite.
If I divide a positive number by a positive number, what kind of number do I get? A positive, right? So it should be positive. If x is positive, the function should be positive. What about if x is negative? If x is negative, I take a positive number, namely 1, and I divide it by a negative number. What am I going to get? A negative number. If I divide a positive number by a negative number, I get a negative number. So the function should be negative to the left of the x-axis, and it should be positive to the right of the x-axis. And if x is getting really, really big, what's happening? If x is getting really, really large, the denominator is getting huge. So the function is getting closer and closer to 0. Okay? So this is what the function 1 over x looks like. This is one of the ones that we need to memorize. So how can we do the transformations? Let's start by doing the horizontal shift left 3. So the next graph I'm going to do is going to be the shift to the left 3. So I'm going to do not 1 over x, but 1 over x plus 3. Let's see what that would look like. Well, the horizontal shift left 3 is going to do what? It introduces a new asymptote. Instead of having the vertical asymptote at x equals 0, I'm going to have a vertical asymptote at x equals to what? Should be -3, right? Because that's what would cause the denominator to be 0. So instead of having a vertical asymptote here, okay, I'm going to shift it over 3. So this is the line x equals -3. And then, of course, the other side needs to go with it, right? Move everything up, pack everything up and move it over to the left by 3 units. Okay. Now to do the vertical stretch, what would I do? I just need to multiply the height of every single point on this graph by 13. So 13 over x plus 3 is going to look like this, but I'm going to multiply the heights by 13. So instead of having like height 1, it's going to have like height 13. So it's going to be more like, probably more like this, okay? Something like that. In fact, I should move this even further out. Right? Like this. Okay, so the heights get bigger faster. All right, and then finally, vertical shift down 4. What are we going to do? We're just going to move it down 4, right? So we're just going to take that whole same picture. And we're going to move it down 4. So instead of having a horizontal asymptote at y equals 0, where's the horizontal asymptote going to be now if we move it all down 4? The horizontal asymptote should be y equals to what?
0.
Well, in this case, it's y equals 0 when we just do the original function. But if we take the whole function and we vertically shift it down 4 units, then the horizontal asymptote will also be shifted down 4 units. So instead of being at y equals 0, where would it be? It'd be at y equals -4, right? So we're going to have an asymptote down here at, so this is the line x equals 3. This is the line y equals -4. And our function is going to look like this. Okay. All I'm really looking for in terms of the vertical stretch is an exaggeration of the height, okay? So this is basically what this looks like.
Would you be looking for like any exact numbers for like the stretch? Or?
No, I don't think so. Okay. So that's how we graph it as a transformation of 1 over x. Let's see how we would graph this normally. Well, f of x equals to what? It equals -4x plus, plus 1 over x plus 3. We can immediately identify all of our things. What are our zeros? Our zeros are going to be when the numerator is 0. So in this case, the numerator is 0 when x is a fourth. And then what do we have? We have a vertical asymptote at x equals to -3. Do we have a horizontal asymptote? what determines whether or not I have a horizontal asymptote? Yeah?
The powers in the numerator and the denominator.
Yeah, the powers in the numerator and the denominator. What's the biggest power of x in the numerator? 1. And what's the biggest power of x in the denominator? 1. So they're the same. What is that going to mean for our horizontal asymptote?
It's top divided by bottom.
Yeah, we take the coefficient of the highest power in the numerator and we divide it by the coefficient of the highest power in the denominator in the case where the powers are the same. So remember, if degree of the numerator is bigger than the degree of the denominator, then we have no asymptote, no horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then we take we take an, which is the coefficient here, and we divide it by bn, which is the coefficient here. Okay, so in this case, it's -4/1. So we get a horizontal asymptote at y equals -4, right? That makes sense. We had a horizontal asymptote at y equals -4 from before. Okay, so that's our horizontal asymptote. Let me move this up here. And the other case, by the way, was if the degree of the denominator is bigger, right? If degree of denominator is bigger than the degree of the numerator, then what's going to happen? What will be my horizontal asymptote?
0.
Y equals 0 will be a horizontal asymptote. Why? Because the denominator has bigger degree. When x is really large, if the denominator is like something like x squared and the numerator is something just like x squared is going to be so much bigger than x that this number is going to be really close to 0. So that's what happens if the denominator has larger degree. So if the numerator outweighs the denominator, no asymptote. If they have the same degree, we check what are these coefficients. If they have the denominator has a bigger degree, then we have y equals 0 as a horizontal asymptote. So this is what our picture is going to be, right? This is what our picture is going to be. So we can draw it in the following way. I guess we can do one more, which is the y-intercept. Y-intercept is going to be what? When I plug in 0, I get 1 on top and 3 on bottom. So 1/3. So here's 1/3. Okay, and then we know that we have a vertical asymptote here and a horizontal asymptote here, and we must pass through that point, right? So we know it's going to look something like, a little something like that, probably. And we pass through the x-axis at, hello, can't move, there we go. Where's our 0? Our 0 is x equals 1/4, so here's 1/4. And then we get closer and closer to -4 as we go out. And then on the other side, we know we should have opposing behavior. Why do I know that I should have opposing behavior on the opposite side and not same behavior? Well, it has to do with the multiplicity of the 0 in the denominator. The multiplicity of the 0 x equals to -3 is 1, which is odd. Odd multiplicity, we have opposite behavior. Odd goes to op, okay? Odd multiplicity, opposite behavior. Okay, so that's pretty much how you could graph it using the other approach. So, the 0? Oh, so how do I know that this function is going to be 0 when x is 1/4? Can anyone explain how I did that for Chris? Sorry?
Set the numerator equals 0 instead.
Yeah, so if I have a fraction, when is the fraction going to be 0? It's when the numerator is 0, right? 0 divided by 3, that's when I get 0, something like that, right? So the way I found out that the fraction would be 0 when x is a quarter is I took the numerator, which is negative 4x plus 1, and I set it equal to 0. I know if the numerator is 0, then the function is 0. So if I plug in negative 4x plus 1 equals 0, and I solve for x, so I'd get 1 equals 4x, and then I would divide both sides by 4, and I would get x is equal to 1/4. Does that answer your question?
Yep.
All right, sweet. Any other questions on this?
Domain and range.
Yeah, we're going to get to that in a sec. So let's talk about that next. Oh, well, are there any other questions on what we've done so far? Yeah? Do you have one? No? You have one?
Okay, so whenever I was doing it, like on the homework,
Mm-hmm.
it has like the chart where you plug in the values on each side of the asymptote. Will that always work? Like, is that the same thing?
Yeah, so,
Okay.
I mean,
Because I know it's more work. I just don't know, because like obviously since it's not negative, it's not going to be flipped or anything. So can we just like look at the graph of the parent function and then just know that it's going to be the same shape, or do we still need to plug in those values no matter what?
well, you know it's going to be the same shape if you know it's going to be a transformation of the parent function. The only exception to that is if you have a reflection, then it's not going to be the same shape. It's going to have a shape like this, right? So you need to keep that in mind. But generally speaking, yes, you can do it that way. And if you know that it's a transformation of this, then you can say no, that the behavior on both sides is going to be opposite, for example, right? So if you have that, then yes, you can use that. What you can also do is a modification of the test point method. You can check, well, I know that the function will always be on one side of these two asymptotes. There's no way for us to like cross the asymptote, right? So what's going to happen is you would have something like -3 on here, and you could pick a test point from each region. Like, you know that the test point 0, when you plug it in, gives you f of 0 is equal to, what, 1/3, which is larger than -4. So you know that you're going to stay on the top side of this asymptote. Is that clear? And then you could test the other side. You could pick something like -4. If you plug in -4, then you'll get some number down here. You'll see f of -4 is something which is less than -4. Okay, so you know that as you go out, you approach this asymptote from the bottom. Is that kind of what you're talking about?
Yeah.
Yeah, but you need to remember that what goes on the other side of this greater than sign is not the number 0, like you might think with the other test point methods. It's actually the number, whatever this asymptote is. So yes, you can use that method to help you determine what the behavior looks like on each side of the asymptote. Any other questions? These are good questions. Okay, then let's do the next part, which is to find the domain and range. Well, the function is, again, -4x plus 1 over x plus 3. What is the domain going to be? First of all, before we think about the domain of this function, someone tell me what is the domain of a function in like complete sentences. What is the domain of a function?
Isn't it like the x values?
Yes, it is. Well, which x values? All of them?
When they intercept the graph of the x.
So I think what it sounds like you're describing is the x-intercepts. Those would be the zeros of the function. But which x values are going to be in the domain? The domain's going to be a big bucket of numbers. And what sort of numbers am I going to put inside the bucket?
Real numbers.
Real numbers. Am I going to exclude any numbers? What numbers might I exclude from the domain?
Asymptotes.
The asymptotes. Well, specifically the vertical asymptotes. Why do I exclude the vertical asymptotes? Because what I want to put in my bucket, which I call the domain, is all of the numbers which are allowed to be plugged in. Okay? So, the domain is the set, okay, by set I mean bucket, of all possible inputs. Okay, so is my domain gonna be all real numbers for this function?
No.
No. Why?
Because we have a vertical asymptote of, wait, no, horizontal asymptote of -3.
Well, we do. It is a vertical asymptote. I think you're right the first time. But yes, why is that a problem for the domain?
Because it's like on the number line of it basically, and if we can't have anything on that line, we can't.
Yeah, so the vertical asymptote is never touched, which the reason that the vertical asymptote is never touched is because you cannot plug -3 into this function. What happens if I plug -3 into this function? I would get on top -11, and on bottom what would I get? If I plug in -3, I get 0 on the bottom. So I must exclude the number -3 from the domain. So I'm gonna set minus, you can do it this way if you want, and take out -3. Or you can say it's -infinity up to -3, and then union 3 to infinity. Or you can say x is not equal to 3, -3. Sorry, -3, and then x is not equal to 3, and x is a real number. Something like that. Okay, 3 different ways of saying it. 1, 2, and 3. Okay, so that's the domain. So the domain is the set of all possible inputs. What is the range?
Set of all possible outputs.
Yeah, is the set of all possible outputs. Let's take a look at our function here. Are there any outputs which the function will never achieve?
Y equals -4.
Yeah, the function height will never be -4. Okay, the function height will never be -4. But every other height, you can find an x value which gives you that height, okay? You just need to go over and see, that height is hit, that height's hit, that height's hit, that height's hit, this height is hit, this height is hit, this height is hit on the other side, and this height is hit on the other side, and so on and so forth. But there's one height which the function will never achieve, and that is the height y equals to -4. So the range, I would say, is -infinity up to -4, union -4 up to infinity, or you could say all real numbers except -4. Okay, so that's the domain and range. Any questions on domain and range? I think that it's that I have a ton of students who struggle with the idea of domain and range and struggle to put into words like what is the domain of a function, just like using a sentence. I think it's tricky because what it requires you to understand is that, look, there are rules for these functions. Sometimes there's things which we cannot plug into a function, right? If it causes us to divide by 0, and what's the other thing that we don't want to do? We don't want to divide by 0, and we don't want to do one other thing.
Take the square root of a negative number.
Very good. Adeline hit the nail on the head. We should not take the square root or any even-powered root of any negative number, okay? So, what I want to describe is like if I gave my friend like a present of this function. Like, here's this function. I got it for you. How nice it is. But by the way, don't plug in -3 because if you do that, it'll break, right? I want to describe for my friend what is the like allowable inputs, right? Okay, if I gave my friend like a juice machine and I was like, I want to express to him that don't put carrots in the juice machine because it'll jam. Something like that, okay? So we need to have the list of all the numbers we can plug in. But the problem is, you can't possibly list them all, right? Because there's infinitely many of them. So we use this notation to say, well, as long as the number is, well, actually this notation we use, as long as the number is bigger than negative infinity and smaller than negative 3, or if the number is between negative 3 and infinity, you're okay. You'll be able to plug that in. Okay? So the domain is the set of all possible inputs, the list of all possible inputs. And the range is, of course, all of the possible outputs that you can get. Are there any questions on domain and range? Okay. Then that's this problem. So was there anything else? Oh, identify vertical and horizontal asymptotes. We already did that. Okay, so that's pretty much all of that problem. Any last questions on rational functions and graphing rational functions and finding their asymptotes and the like? Yeah.
Would there ever be a question where if we graph one versus like we would just do a calculation for it, would we ever like have a like no vertical or horizontal asymptote?
Could you have a rational function with no vertical and no horizontal asymptote? You could. You could have. Well, you could have. Yeah, you could. Let's see that in action. I think I can cook up an example for you. Let's see the function f of x equals to x squared plus 7x plus 12 divided by x plus 3. Okay, so let's graph. Okay, let's graph. So, my question for the class, and it's a trick question. Well, it's not a trick question. It's just a question. Is there a vertical asymptote at x equals to negative 3? That would make the denominator 0, right? No. Why is there not a vertical asymptote at x equals negative 3 for this problem?
FOIL, it cancels out.
Yeah, if you factor the numerator, what would we get? X plus 4 and x plus 3, right? Sorry, did I do it wrong?
No, it's right. Just like that's evil.
So, and then x plus 3 here. And then what happens? These two cancel. So, follow-up question. Does the graph... Well, we cancel these two, right? So what are we left with? F of x is just x plus 4, right? So what does that look like? Does the graph look like this? Well, x plus 4, that's just y equals x, shifted up 4 units, right? So I go 1, 2, 3, 4, and I do a line, and done. Who says no? Be confident. You're right. What's up? Yeah.
I was just saying no.
Oh, you were saying no. Okay. Can you explain why? Why no? I canceled those terms. I got x plus 4.
So if it's just x plus 4, wouldn't that just be like horizontal line?
Well, if f of x is equal to x plus 4, right? Remember, y is equal to f of x, which is equal to x plus 4. So y equals x plus 4 is a line, and it looks just like this, but there is something else wrong about it. What have I failed to account for? Is almost right. We're nearly there, but there's something. I mean, x plus 4 does look like this. I've drawn x plus 4 correctly, but I have sort of failed to take into account where we came from, haven't I? Right? So the problem is, okay, you can do this cancellation, but there is one situation where you cannot cancel like this, and that is when x is equal to -3. Okay? Because what would I get on the original function if I plug in -3? I would get on the top -3 squared plus 7 times -3 plus 12, which would be 0. And then on the bottom, what would I get? Also 0. So, do you think I'm allowed to plug in -3 into this function? No, so -3 is not in the domain of this function. Okay, -3 is not in the domain of this function. So, this function will be equal to x equals x plus 4, provided that x is not equal to -3. So how can I fix my graph?
Put a little hollowed out circle at.
Yeah, I need a hole right here. Okay, so not like this, but rather like this. Because x should not be equal to -3. So I just make this line look like so. It should look like x plus 4, except for that one tiny snag, which is that we have to remember where we came from. And where we came from was this function. Yes, this function is equal to this function for every value of x except -3. If it's -3, we get 0 over 0. Yes?
Why is the whole, like, at 3? Like, why is it on the positive side if it says x cannot equal to
Oh, I'm sorry. I put the hole in the wrong spot is why. Sorry. Yeah, it should be at -3. Thank you for correcting that mistake. Yeah, so it should look like this. Sorry about that. I don't know. It should look like this. Yeah, don't be afraid to just yell at me if I make a mistake and be like, hey, you messed up. Okay, so yes, we should. The important thing is we should have a hole, and also the hole should be in the correct spot. So I'll do my half, and you do your half, and we'll get it right together. All right. Any questions on this example? So this is an example of this is a rational function, and not only does it not have a horizontal asymptote, not only does it not have a vertical asymptote, i.e. you think maybe there's a vertical asymptote at x equals -3, but there's actually not. But also, there's no horizontal asymptote. Why is there no horizontal asymptote?
There's no number you can plug in to make it 0.
There is no number that I can plug in to make it 0, but what specifically for a rational function told us whether we were going to have a horizontal asymptote or not? Yeah. The numerator, what about the numerator and denominator?
Powers.
The powers, the degree. What's the degree of the numerator? 2. What's the degree of the denominator? 1. This is why we don't have a horizontal asymptote. This is why our function doesn't look like, say, like that, or like, we don't get closer and closer to 0. Why not? Because when x gets really big, x squared will be so much bigger than x that it's not even funny. No, not that it's not even funny. It's just that they're incomparable, basically. Okay? So that's why we don't have a horizontal asymptote. So, here's a rational function with no vertical asymptote and no horizontal asymptote. Okay, any other questions on this example? No? Okay, then we did transformations. How about compositions of functions? Let's talk about compositions. See if we can find a good problem here. All right, let's do this one. So it says f of x is square root x and g of x is x minus 13. And it says find f plus g of x, f minus g of x, f g of x, f over g of x, and we're also going to do f o g of x, and g o f of x, and g o g of x. So, this is where we're going. So let's just start at the top. How do I do f plus g of x? Go ahead. You're not disrupting me. It's fine. How do I add two functions together? Do I need to do anything special? All right.
Just put them together, I guess.
Yeah, so if I'm adding them, okay, this is the notation we use, but what we really mean is f of x plus g of x. Okay, so this is a new function whose height at a given x value is just whatever I get when I take the height of the f function and I add it to the height of the g function. If I add those two things together, I get the height of f plus g of x. So in this case, I would just take the two formulas, right? I know what f of x is. It's square root x. I'm going to put it here. I know what g of x is. It's x minus 13. I'm going to put it here. So I get square root x plus x minus 13. Okay, that was pretty easy. Now let's do another one. Let's do f minus g. Well, as you know, subtraction is nothing but fancy addition. So we're going to rewrite this as f of x minus g of x. Okay, so I'm thinking I should subtract these two functions. So if I did that, I would get square root x, and then not plus x minus 13, but minus, and then x minus 13, right? Are we happy? No, we're not happy. What went wrong? I didn't distribute the negative sign. I was supposed to subtract g of x, which means I should have subtracted all of this, okay? There's a big difference between having parentheses here and not having parentheses here. The big difference is that in this case, we are adding 13. If I don't have the parentheses, then I'm subtracting 13. So I need to have my parentheses. If you want to then distribute it out, we get square root x minus x plus 13, okay? All right. How about fg of x? What should I do for that one? Yeah, I just take f of x and g of x and I multiply them. So what do I get? I get square root x times x minus 13, which if you distribute it out, you get x root x minus 13 root x. Okay, so that's that. How about if I divide them? Well, I just divide them. F of x divided by g of x, right? And if I do that, I get square root x divided by x minus 13. Any questions so far? Yeah, a little slower, sure. So for f plus g of x, okay, actually for all of these, f plus g, f minus g, fg, and f over g, all we actually do is this notation just means that you take one function and you add it to another, or you take one function and you subtract it from the other, or you might take one function and multiply it with the other, or take one function and divide it by the other function. Okay, so f plus g, f minus g, fg, and f over g, I think are, for the most part, fairly straightforward. Where it gets a little more complicated is with the f of g of x, okay? If I write notation like this, where I do one of these little circles in between, What does that mean that I am supposed to do? That's notation. Someone translate it for me? Yeah, which one are we going to put inside of which one? Which one goes on the inside? Yeah, G goes inside of F for this one. So we do, it's, the way you can read it is literally F in this little O you can think of as being of. F of G of X. So that would look like F of G of X. Like so. Okay, so from here it gets a little bit trickier. So what I need to do in order to get my formula is I need to remember, what is G? Well, G is the function x minus 13. So I can replace it by x minus 13. So I can rewrite this as f of x minus 13. Okay, so all I've done here is I've replaced g of x by the thing that it is equal to. I can always replace something as long as I have an equal sign, right? I can replace it by whatever's on the other side of the equal sign. And now this is the real tricky part. What am I going to do here in order to simplify this? F of x minus 13. What should I do? Yeah, okay, so what Sully said is just right. We're going to plug x minus 13 in up here, okay, in the function f. So if we did that, what would it look like? Exactly, just like so. Okay. So that's how we plug one function into another. What about g o f of x? Is it going to be the same thing?
No.
No, it's not going to be the same thing, okay? It's different than f plus g, right? If I do f plus g, this is the same as g plus f, right? Because addition you can do in any order, right? 3 plus 5 is the same as 5 plus 3. But when we compose functions, the order does matter, okay? Order does matter. So this one is going to be, you can read it like g of f of x. So that would look like this, g of f of x. So that would be equal to what? Now I'm going to replace f of x by the thing that it is equal to. So I'm going to do g of, what goes in my parentheses here?
Square root of x.
Square root of x. And now what do I do? This is the hard part. I got to take square root x, and anywhere I see an x in the function g, I'm going to replace that by whatever's inside the parentheses here. So what will that look like this time? Yeah, square root of x minus 13. So you can see these two things are very different creatures. Okay, so the order does matter. Okay, whoa, this one's weird. G of x? What is that supposed to be? Can I do that? Is that allowed? If we say no, we should always have a good reason for saying no. I'm sorry. Come on in. Are you... Okay. I don't understand if they need this classroom. I'm pretty sure I have it for another 20 minutes. Okay. So that's g of x. So what is it? It just means I plug g into itself, which, let's just see if it'll work out, okay? Let's see if it'll work out. Well, I can replace g by the thing that it's equal to, right? I get g of x minus 13. And now what am I going to do? I'm just going to replace x by whatever is in the parentheses, okay? So what would I get? I would get x minus 13 minus 13, which would be x minus 26. Okay, so successive, you can think about this in two ways. You can think about it as a composition if you want, or you can think about the g function as a machine whose job is to subtract 13. What if I take a number and I plug it into the g machine, which makes it less 13, and I take that number and I plug it straight back in, I get minus 13 again. So all told, I've subtracted 26 from the initial number, okay? So one final thing I want to discuss is what would I do if I wanted to do FOG of 3? What would I do if I wanted to do this? Yeah? Yeah, I'm going to plug in 3 where? For x in here. Yeah, that's where I'm going to put it, right? So that's all I would do is once I have the formula, I can just plug in. But what happens when I do that? Are we happy?
No.
No, why are we unhappy?
Because it's going to be square root of negative.
It's going to be the square root of negative 10, right? So this is undefined. Okay, so a lot of times with these composition functions, there's a bit of a sticking point with the domain, okay? Which is that the domain of a composition, if you remember, we had a heinous-looking slide discussing that. The input needs to be okay to plug into the first function, and moreover, it must produce as an output a number which is okay to be plugged into the f function, right? So if you have compositions of functions, there is a little bit of a, we need to just be a little bit careful about what we plug in. But otherwise, we just, if we want to do a number, just plug in the number, right? Okay. Well, that's all I have. I think I'm about out of time, and I need to relinquish this classroom. So,
Is this test going to be hard?
the test is harder than the first test.
That's horrifying to think about.
But I think that if you're having a good time on the homework and you know what you're doing and you're able to do a decent, like most of the homework problems without any help, then you should have no trouble.
I'd like to formally apologize for my grade now.
That's okay.